Everybody understand graphs? Nodes, edges. We had the depth first traversal, breadth first traversal. What else do we have? Minimum spanning tree. Okay, everybody understand that? Directed, undirected, et cetera, et cetera, et cetera. Okay, so we got a couple more algorithms that I want to cover. They're going to deal with trees, or graphs rather, specifically. Let me get this thing to remotely work, but it doesn't seem to want to work when I want it to work. Okay, so the algorithm we're going to look at is going to be called the shortest path. And to understand shortest path, what we're trying to do is we have a graph and we have some directed edges. They don't have to be directed edges, but they are in this case. Oftentimes they are, oftentimes edges are directed. That means that the signal or the information only travels from one node to the other. It doesn't necessarily travel back, unless there's sometimes if A is going to communicate with B and B with A, there could be another edge going from B to A in a directed graph, and that's not unusual. Okay? So let's say I want to go from A to G. That's the shortest path. Well, I can go from A to D, right? And then I can go to G. That's pretty cheap. I can go from A to C, from C to E, from E to F. I'm stuck. From E, I guess I can go here. How do I go to G? A, B, G, A, B, D, G. There's two different ways to get there, which is the shorter path. A, B, G. So if I were to try to get the shortest path from A to G, I probably should just go from A. Can I go directly to G?
No.
Why? Because there's no edge. If I put this on a matrix, and I did the transitive closure, what would be the value of the transitive closure matrix on the intersection of A to G? What would be the value in the transitive closure matrix from A to G? Intersection A to G. There's going to be a question. Is it going to be 0 or 1?
1.
So okay, 1, what does that mean?
There's
There is a way to generate a path from A to G, which it has 1 or 0 or more moves. Obviously, since A and G are different, we're going to say 1 or more moves. Now, let me ask you a question. If I were generating this path, let's say, this is kind of a test question. I guess I'm thinking test, so I'm trying to get you to think the way I might think in the future as I'm covering the material currently. So when I look at it, I go, oh, there's a question. So you guys kind of know how I think a little bit, get an idea. Some of you like the way I think, some of you hate the way I think. That's all right. I like the way you all answer my questions. That's always good. So let's suppose I wrote a matrix, a Boolean matrix representing this graph. We can all do that, right? So let's say I took this matrix and I multiplied it by itself, creating a second Boolean power. Okay? My question to you is, would the connection from A to G have a 1 in it, or would it have a 0 in it?
A 1.
How do people think it's a 1? Seems to be a very popular answer. Okay? And Damien's going to tell us why. Why do you say 1? Because you were very clear about it.
Because Edward said it was a 1.
Excellent answer, but that won't fly on the test. Please see Edward's answer. Okay, that's the correct answer, but what do you think? Why would the second Boolean power from A to G be a 1?
1 indicates that the circuit's open, it's true.
Well, it indicates what? That we have, what is a 1 in M2, the squared Boolean matrix, M2? What does a 1 indicate? That I can go from, if there's a 1 there, it means I can go from I, vertex I to vertex J in 2 or less steps. Okay, what does a 1 indicate in the original matrix? Again, forget about the diagonal. We'll get rid of 0, because 0, it's got, of course I can go from A to A. But what does a 1 indicate in the Boolean matrix M? means I can go from I to j
In one step.
in one step. But a 0 indicates that I cannot go from I to j in one step. When I take this M matrix and I multiply it by the M matrix again, I have additional 1, which we made yellow yesterday on Monday. And those yellow ones indicated those are new connections that I can go from I to j. But if they're yellow in the M2 matrix, that means I can get there in 2 steps. And the reason Edward's answer was correct is because I can go from A to B in 1 step, therefore it's going to be an M. I can go from B to G in 1 step in M, therefore I can go from A to B to G in 2 steps. And that's why that's going to appear in M2. Notice that I can also go from A to G in 3 steps. I can go A, B, D, G. And that's going to be the third Boolean power. But by the time I get there, A to G is already going to be a 1. And guess what? If we have a 1 in any Boolean matrix, that 1 never goes away. Ever. Why? Yeah.
I was just going to ask you why.
That's great minds think alike. That's a great answer. Okay, so who can answer that question? That's a very good question. I thought it was a very good question. So why does the 1 in a Boolean matrix never go away? I mean, obviously, visually speaking, if I can go from A to B, or I to J, and on a graph, then I should always be able to go on that graph, right? If I should be able to go there in 2 or less steps, I should certainly be able to go there in 3 or less steps, etc., etc., etc. So ideally, logically, it should never go away. But why does it go away from the standpoint of the mathematics raising of the Boolean power? Well, let's think about how it appears. So let's say we have a 0 in ij intersection. And now we take the matrix times the matrix, we compute the squared matrix. The 1 appears. The 1 appears. So now this is a 1. So the question is, why is this 1 going to persist in M3? Well, the question is, why did it appear in M2? It appeared, so I to j was a 0. Okay, it's because I can go to some new location k, and k can go to some new location j, and therefore, I now have this 1 times 1, or 1 and 1 is going to be a 1, and that OR is to be a 1 in M2. So the location from I to k is going to always be part of the M matrix. The new matrix M2 is going to now have what? It's still going to have the original k to j. So therefore, when I multiply M1 by M2 producing M3, that same intersection is still going to yield a 1, and that 1 is going to stay. Because I'm not going to lose any connection. I don't know if that helps. Does it help?
Well, I was trying to figure, is there such a thing as Boolean arithmetic?
Yes.
And are we doing,
This is Boolean arithmetic, essentially.
And so is it like in Boolean arithmetic, is there not a carry sometimes? Like if you were to add up a column?
That's if you're doing, of course. So well, Boolean, you could, it would be, but in our case, we're doing very simple Boolean operations. We're basically doing bitwise ands, and then we're ORing a bunch of them. Because of the ands, so two locations have to be a 1 to make a 1. But we have a whole bunch of these pairs. If any of them are a 1, then because we put an OR between them, any one of them turns it on into a 1. So again, if I can go to k, and k can go to j, but I cannot go to j, then, and I can show you this on the board, but it's going to take a little bit too much time. But if I can go from I to k on matrix M, and from k to j on matrix M, then M squared will find that intersection on I to j, because we're going to have intersection of going from I to j. So we will match up when the row I has the kth column, okay, and the column j has the kth row, they're going to match up. And when they match up, it's going to produce a 1 in the matrix M2. And that's going to stay. So that is now going to keep multiplying. So matrix M2 is at least as big as, has everything that M1 has plus some. So when we take M2 multiplied by M1, we haven't lost anything. So just think about this I to k, k to j from M going into M2. That's going to persist. And then we're going to multiply M again by the same thing. And remember, M2 has at least as many ones as the other one. Okay. If 1 can go to 2, and 2 can go to 3, let's say, okay, I'm going to stop here. I'm going to get carried away. All right. So the idea is we're trying to get the shortest possible distance. So let's see. Okay. So what we're going to do is we're going to look at this algorithm. So this algorithm essentially is the breadth first search algorithm. Because what I want to do is I want to do a breadth search traversal. Again, remember how we had the matrix. We were going from A to G, right? I think was that the. Can't flip back quickly. So A to G we're going just a second ago. A to G, either through A, B, G could, okay, so A, B. So when I visit from A, in one step I can go to B. So that means I'm going to visit everybody I can with one step. So if you go back to A, I guess I have to go back. If I go back here, that's not very good. So if I go to A, notice I can visit what in one step? I can go to B, I can go to C, and I can go to D. With a distance of 1. So now we're going to NQ B, C, D. The next thing we're going to do is we're going to DQ what? After DQing A and visiting A, we're going to DQ B. And all the neighbors of B are going to be C and D. So I will visit B, okay, because I've already visited. Now we'll visit all the immediate neighbors of B, which are what? Actually, so let me back up for a second. So first thing I'm going to do is I'm going to visit A, put it in the queue. Then I'm going to DQ it and put all the neighbors of A, which are going to be B, C, and D. So then I'm going to DQ them in turn. I'm going to DQ B first, visit B, and put all the neighbors of B, which are going to be, well, in this case, C, D, and G. Okay, all right? Then I'm going to visit what? C, which is the second neighbor of A, and I'm going to visit C, so I'm going to visit C, and that will be a visit, and then I'll put all the neighbors of C, which is going to be E. Then after that, next in the queue is going to be D. So I'll visit D, so I'll visit A, B, C, D, and I will in-queue F and G if G hasn't been visited, right? Now, once I'm at B, I'll be visiting which nodes? C, D, and G. So therefore, by the time I finish with B, I'm going to NQ G. So G is going to get DQ'd because it's 1 unit away from B, which is 1 unit away from A, therefore that's 2 units. So we will visit G as a node that's 2 units away from A. So when we go to the algorithm, and this is basically, again, this is basically the BFS algorithm with some modifications to keep track of where we are, where we came from. I'll give you an example of that in a second. Oh, now it's working. Very exciting. I don't know what it is. Cannot figure it out. All right, that's very exciting. Okay, so I can stand here. I can join you guys, get a nice perspective on these great slides. Okay, so we're going to have a bunch of vectors. The vectors will simply be like arrays of values for each vertex. So we'll have and initialize a distance vector to -1. So if I have, for example, A, B, C, D, E, F, G vertices, it's going to be -1, -1, -1, a bunch of -1s. And simply that means that the distance vector means -1 means you can either put infinity or -1. Some indication you haven't been there before. Okay, that's the idea there. Now, we're going to visit the start vertex. Start vertex is wherever you are asked to begin. In our case, maybe A. And then we're going to have a distance vector. And we're going to set the distance vector at the location of start to 0, indicating that the distance from the start to the start is 0, which makes sense because you're already there. You're starting there. Now, distance is going to be a scalar or a single value. And that distance is going to simply indicate how far am I right now from the start. Okay, so since I'm at the start right now, distance should be equal to 0. Okay? Then I'm going to initialize the Q, and I'm going to put the start vertex in there. So if I'm starting at A, I'm going to put A only into the Q. So this is very similar to BFS. So now I'm going to loop while the destination is not visited. I think the destination was G. But it doesn't matter, this is general. While the destination is not visited and the Q is not empty. Well, it's not empty because what's in there? Our starting vertex A is right now in there. So I'm going to remove A into V. So V is the current vertex. We'll get the value of whatever in the Q. In this case was A. I'll remove A into V from the Q. So V is the current vertex. If the distance of V is bigger than distance, is it? Is the distance of V bigger than distance? Well, distance of V, which is A, is 0. Is it bigger than distance? The answer is no. So that means I'm currently at V, and the distance from where I am, from this, where I am right now, from the start, is 0. So therefore, what I'm going to do is, while all this is true, I will remove the vertex from the Q. Okay, if the distance is greater than distance, then increase distance, but it's not. So distance stays at 0. So now I'm going to loop, like in BFS, for my adjacent neighbors. For each adjacent neighbor W to V, if W has not been visited, we will set the predecessor vector. The predecessor vector for each vertex shows you which neighbor you should visit before this one. Okay, so we'll set the predecessor of this one to here. Since I can go from V to W, because W is one of the places I can go from V, then I will say you can go to W from V. The predecessor of W is V. So therefore, V will be the predecessor of all of the neighbors W. So if the vertex V can go to these three, then all of these three in the predecessor vector will have a V in it. Okay, now we're going to visit each of these. So we check the V. If it has not been visited, then set the predecessor of W to V, visit W, and set the distance of W, distance plus 1. Since we're currently at V, and we have just visited W, and W is a neighbor of V, then whatever distance is to the current V, add 1 to it because you're going 1 more. So that means when I visit from A, when I visit B, it's going to get a 1 in its distance. I will visit B, and I will set its distance to 1. I will then add it into the Q. So as I go through my neighbors BCD, BCD will go into the Q. Notice the Q is empty right now, but I've just taken the value out, so now I've loaded in with these 3 iterations, I loaded it with BCD. And I've also set the predecessor of BCD with A. And I also set the distance of BCD with 1. Okay, so when I finish all of this business, I'm going to go up here. Now, I'm going to check how I visit the destination. Well, since the destination was supposed to be G, let's say, then I will notice that I have not visited G yet, so therefore destination not visited is true. Q is not empty, true. B, C, D are in there. So I will remove B from the Q, leaving CD. I will remove B from the Q. Now, what's the dist of B? Well, the dist of B was set here as 1. So therefore, if the distance of V, which is 1, greater than distance. Well, distance was set originally to 0, so the answer is yes, it is. So therefore, distance gets bumped to 1, which means as V is now equal to B, the distance from the beginning of B is actually 1. So that means as I visit the neighbors of B, all the W's that are neighbors of B, their distance will be 1 plus 1, that will be 2. So all the neighbors from B will have a marker value of 2. So if any neighbor of B has not been visited, set the predecessor of that neighbor to B. The predecessor of B was A, and the predecessor of the neighbor of B is B. So let's say that W is equal to J. So that means the predecessor of J is B, and the predecessor of B is A. Now if J happens to be my destination, then that means you have arrived at J, that means before you were at B. And if you're at B, the predecessor of that is A. So if you want to go from A to J, you need to, you can start at J and then look at the predecessors to get you there. So we're working the predecessors backward. backward towards the start. Notice that when, so we will visit all the neighbors of B, and we'll mark them as visited and all that kind of good stuff. So now, once we finish with B, we're going to go up here. Let's say the destination is not yet visited, so at that point Q is still not empty. I still have what in there? C and D plus whatever neighbors I have not visited that were in Q. So it's going to include C and D plus any neighbors of B which were not visited before. So therefore, I'm now going to remove B from the Q. What's the value of B? Which vertex is it? Which vertex is it? A, and then we put B, C, D. We just removed B from the Q, that was B, visited B's neighbors. Now? Okay, so we're going to remove C from the Q. So V has a value of C. V has a value of C. What's the distance of C? Well, the distance of C was set a long time ago at 1. And what's the value of distance with this? 1. That's 1. So therefore, when we're at B, B is still 1 away from the beginning. Don't bump the distance because B is equidistant from A, as is B, as will be D. So as we process B, C, D, my distance is still 1, 1, 1. We will not bump that value until we visit the first unvisited neighbor of B. Okay? Does that make sense? And as we visit every neighbor of B, C, and D, that value, which will be at that point 2, will not switch until we visit the first neighbor of B, which has not been visited. Okay? Does that make sense? Okay. Now, so these vectors are going to get created. We're going to look at an example in a second. Let's look at finding the path. So we're going to assume that this algorithm is going to do its thing. It's going to run its course. We're going to fill the distance vector. We're going to fill the predecessor vector. And we also have an unvisited vector. And unvisited simply means that we'll just check it off each time. So that means we never are going to arrive at another vertex twice. Again, we don't want to loop. So the vectors are done. So let's think about what's going on here. We're going to increase the distance to distance plus 1 after finishing the algorithm. Let's see why we would do that. So basically, let's say we're visiting a vertex V. And one of the W's, which is a child, or not a child, but a neighbor of that vertex V, is a W. The distance right now, the distance variable is the distance that V is from the beginning. So when I visit a W, the value of that W will be distance plus 1. Suppose that W is actually the destination. Then the destination, let's call it J again. So the destination will have a value of J of distance plus 1 in its DIST vector, distance vector entry. When I come up to the top of the loop, destination not visited will be false. I will drop out of the loop. So I'll drop out of the loop while the distance scalar number is not the destination J, but its predecessor. So therefore, I need to increase the distance by 1. Does that make sense? It's as simple as that. Now, I'm doing this whether or not I was able to reach. It's possible that J is unreachable from A, or from some starting vertex. So I'm going to increase the distance to distance plus 1, pretending that I've reached it, but then I have to check. If destination is not visited, then it doesn't matter what distance is equal to. It's invalid. So therefore, if destination is not visited in the unvisited vector, then I can say destination is not reachable from the start. I'm done. Otherwise, I'm going to now create a path. And the path will start at index 0. So path will now be how do you go from A to destination, from start to end. So path 0, the initial spot will be start. Now I will go to path subdistance. So I will put in the last element, and that will be the destination vertex. And then what I will do is I will go from distance minus 1 down to 1. Fill in, so path 0 is here. Okay, path distance is here. Then I have to fill in all of the previous steps. And the way I do that is for each location I, in between the destination and the start, I put into the path sub I the value of the predecessor of the path of I plus 1. So as I want to put in here the path value, I will look at the predecessor of this value. So now you can see how the predecessors work. And then I'll show you a specific example so you can see how it works. Okay, so let's say on our example, I want to go from A to E. So we're going to go from A to E. Where's E? So E, you can see I can go to E a variety of ways. I can go here like this. I can go to, I guess I can't go this way. Yep, in this way. I make E very popular. This way, lots of ways. So I'm trying to go from A to E. So the first thing I'm going to do is I'm going to initialize the distance vector to all negative ones, and then immediately A, since it's the starting location, gets a value of 0. If my starting value was D, that would go 0, everything else would be negative 1. So this means what? This is not only the distance vector, but also can be used as the unvisited vector. Because if there's a minus 1 there, it means I haven't been there before. Otherwise, I would change the value. The predecessor vector right now initially is empty. And the visited vector, again, it's almost like the complement of this one. Basically, 1 means that it's not negative 1. So you really kind of don't need this. You can use this, but this is just exclusive. So the distance is 0. Q includes the value of A. And then we take it out of the Q, and V becomes A. That becomes the first active vertex. It's the start. The Q becomes empty temporarily. And the W takes on the values of B, C, D. Okay. B has not been visited, so we mark the predecessor of B with A. C has not, now I'm skipping a loop here, because this is a loop, right? C has not been visited, so we mark the predecessor of C also, A. And D has not been visited, so we mark the predecessor of D also with A. So I'm just kind of skipping. But basically, once we are considering B, we mark this predecessor here, we visit B, and we set the distance of B equal to the distance plus 1. Remember, distance was initialized to 0, so we get 0 plus 1 is 1. And the Q includes now B. We put B in the Q. We're now going to the second iteration. The second iteration says C has not been visited, so set the predecessor of C to A, which is still the active V value, visit C, mark the distance as distance plus 1, which makes it effectively 1, and add C into the Q. Do the same thing with D. So now the Q, in my 3 iterations of that loop, put BCD in here. So now I'm going to come out here, now I'm going to check, did I actually visit my destination? Well, destination is what?
E.
Destination is E. E has not been visited. So you can see that right now the visited vector is going to contain A, and then what? And then we're going to have B, C, D. These are going to have 1, 1, 1, and then 1, 1, 1 here for different reasons. So these ones means that it's been visited. These ones means it's a distance from A. Okay, so now my Q contains B, C, D. I'm in the outer loop, have not visited the location, so therefore this is the situation we have here. Notice the predecessors are here. Okay. Now notice that if my destination was D, I would have quit the loop. And then I would have known that my destination D has been visited, and the predecessor is A. Since that's the start, that's the path of AD. Okay, but I haven't quite made it yet. So I'm going to take out of the Q the first thing that's in there, and that's a B. So B comes into the next active vertex. Q includes now only C and D, which is fine. The distance equal to 1 increases, because the distance of B is 1 from A, and distance is equal to 0, so therefore it's greater than, so we increase the distance scalar to 1. And now we look at the adjacents to B, which include C, D, and G. So in the first iteration we try to do C, but C's already been visited, so we just short circuit that loop. We go directly to D. D was already visited, so now we go directly to G. So once C and D come up, we basically don't have to do anything with those guys. So D was already visited, so W is going to be G. G has not been visited, so therefore we set the predecessor of G to B, which is the current vertex B. We visit that vertex, and then we set the distance of it equal to distance plus 1, which makes it 2. And now we put C, D, and G in 2. And that's what my vectors look like. Again, these are the visited nodes. These are the predecessors. And when I check to see whether I should stop, the answer is no, because destination has not been visited yet. So that's one of the conditions for stopping. E has not been visited. There's no guarantee E is going to be visited, but we know it will be in this case. So C comes in. The Q includes only D and G. The distance stays the same. The neighbors of C are E and G. E has not been visited, so we mark the predecessor of E with C, which is the current vertex B. We visit this E, we set the distance of E to 2, and we add E to the Q. Now, the next, what do we do next? C comes in, D and G. So what's going to happen here? Oh, sorry, E and G. So we did E. What about G? G's already been visited, right? So that means we finish the 2 iterations here, and as we go up here, destination not visited now is false. We drop out of the loop. We drop out of the loop, and that's the final state of the tables. So notice that we never made it to F. We visited everything else except for F, I suppose. And this is the predecessors. And notice that 0 means that F has not been visited. So now we're going to do a path table. So the path is going to get, basically, you can see that the distance is equal to 1. So the distance sets equal to distance plus 1, which makes it equal to 2. And so into the location 2 for the path, we put the destination. Into path 0, we put the start. And now we only have one value to get, and that value is going to be gotten from, we need to put whatever node is the predecessor of E. And the predecessor of E is C. So the path is going to be A, C, E. So now we can go, that's the shortest path. That's the idea. Any questions about that? So it's the shortest path algorithm. So I could ask you some questions about this algorithm in terms of some complexity questions. Okay? Sometimes I can ask you questions that have, I try to stay away from very, very general hard questions for average complexity, but I can give you some assumptions. For example, that we have on average 2 edges per node.